restrict each talk to 5 minutes as much as possible because we usually need to discuss. Okay.
Okay, so just starting off, I'm going to show you how to download MATLAB. How I did it is just looked up MATLAB and DSU download. Then I clicked up here, get software, and then you'll go down, it'll bring you to a spot that you can just click to download the software. So if you're doing it with NDSU, you'll then just type in your NDSU username and password. Then it'll then bring you to what version you want to download. I just did the newest version of MATLAB. And then you wait for this to fill up on the bottom, click that. And then once you open that, it'll have you sign in with your NDSU email. Remember to do SU instead of US, because if you do US, I don't think it'll work. But I know SU does. Then you check which folder you want it to go to, which I don't think that, or I don't think it matters where you send it to really. And then you click what version you want to install. And so I just click MATLAB and then you're ready to install it. I didn't click to get installed because I already have it downloaded for other classes, but that's all you really need to do. And then Dr. Keelan asked me to show some progress made with the density of states. And David helped me out with this a bit, but this is the system we're modeling. And now, if you remember from last time, this looks similar, but now we're doing it with spin and something different from the what we wanted to get. We wanted this to be, well, that's my mouse, but we can see it on the very right side at 19. That should be up to 2, but it's only to 1. And after looking at it, we still don't really know why it's only goes up to 1, even though when looking at the K points, it should be at 2. And I don't know why that's not being displayed on the graph. Any questions about MATLAB installed or?
Oh, you're done.
Yeah.
Okay. So it seems like a quite simple thing, but just in case if anyone was missing it or had some errors, I think you saw that it is doable, right? I know that those of us who are not affiliated with this university may need to go to their school, so evaluation version for a short time for commercial is very undesirable, because most schools provide access. Many things. Can you please cover by words if there is not in the slides steps? What do you need? Just describe your experience. What do you need to make this spin-polarized?
Yeah. So it's fairly similar. So what you do before you end up printing the code, do more outcar, and then you go.
And you're not answering to me. You're teaching the rest of the audience.
Yeah, so you just do more outcar like you did last time. I'm trying to find where. Oh, here's your spin component key points. Spin component 1 is up. Spin component 2 is down. And then gives you a bunch of other information. You then copy and paste that information in a folder, states up and states down. And then you end up doing the dash bin, dress dots off, you enter in your information like usual. And then you do it the same with down. And then still enter in that information.
Okay, so you have several lists of orbitals combined into files. Two lists in each of the files.
Yeah.
Does it look surprising or natural to the rest of us? So in comparison to what most of us were doing in the past, he used more than one K point for spin up, more than one for spin down, because it is a point for the system. The rest is the same as everyone was doing.
And then one thing to notice that was different with David and I found that didn't seem to be matching up would be at like around 19 we have two band energies, but in here it's only showed as like being one.
Okay, so the peaks are not resolved, they merged together.
Yeah.
Okay. It happens.
Okay. Which that was something that was confusing. It wasn't showing in this. Thanks for saying that.
Okay, other more questions to William? Questions to turn Adam for yours. So there is a very relatively simple programming exercise to do high throughput reading or writing of many files with different names. And for the beginning first steps of programming, typically it's a little better. In my time, I was scared of by this.
Okay.
Not unmuted there.
Yeah, so I'm just going to be going through the script that you use to kind of process the coupling files. Basically, what you need to modify in it to be able to read these coupling files, and also what you need to specify for the energy path. So, yep. So you need your coupling number files. You can just download those to your computer, and the energy path file. These are using the correlation V7 MATLAB script, and need to modify range, or you need to modify this script to include the range of states that you have in your energy box. So that's the lowest and the highest orbital, and then your HOMO as well. And then also the method. I'll go through the method in which MATLAB uses to read coupling files and why you need to use a different method across different runs. So yeah, Omin is going to be your minimum orbital. Omax is going to be your highest orbital, and then your HOMO is going to be your HOMO, of course. And you can manually find these just with more energy popping for your photon. Just read the lowest number and the highest number, and then the HOMO. You should be able to find that. Now, this is kind of the main part. So how the script works is it reads the coupling files as it reads this first part, right? Coupling dot, and it grabs the number at the end. In the case of this down here, that's what that is doing essentially. And so it reads that as number. MATLAB really isn't good at reading a number with the 0 in front, as that number. So if it was coupling.023, this piece of code right here, it would read that as 023, and it's going to say, oh, not 23. So it's not going to understand it. Coupling 009 would read not as the number 9. So essentially, you have these 3 separate things. These top 2 are kind of commented out in this slide, but you have these 3 things. Theoretically, you can go for K1 to 9, or the file 1 to 9. This is what you're going to need. It's going to be coupling dots 0, 0. So you're omitting that first part, and it's actually just going to read that 1-digit number. 10 to 99, 2-digit numbers, you're going to have coupling dot 0 right here. And here's the coupling dot that I showed for this last one. Yeah, if you don't have 999 coupling files, you just specify how many you have. And you can modify the range if you're trying to say from like 50 to 75 as well. Just for those, you can specify which one you have in the code. So, yeah, questions?
Great, please join me in thanking the speaker. So anything was not clear and we wanted to learn about this process to reduce. It's true. Chat line.
Could you go over how to fix like when it has the 0 in the front again?
Oh yeah, I'm sorry. That was kind of might have breezed over that one, but yeah. So here it's just going to read it as 023. This coupling dot, right? And this you're going to uncomment this and comment this out. So what that would look like is it's going to be this middle one that you're going to uncomment because it would omit this first 0 and it would just read 23 as 23. For any 2-digit number. Does that make sense? Yeah. These are just parts of the thing that you can comment out or recomment. Rectangle should actually be like over here because this is not kind of related to these. So, yeah, thank you.
So everyone is happy. But thank you once again. So London, will this share screen? So now we go to a little bit more background of what we are doing in addition to practical steps.
We'll see if I can here. There might be a security issue, but I do have admin rights on this computer. Oh, Jesus. So I'm going to have to quit Zoom and reopen it to be able to share my screen.
Okay, let's do it. We'll wait.
Okay, I'll be right back.
Okay. And if things will not work, we will arrange maybe projecting his slides from one equipment and he will be just the voice behind the wall. So what we are doing is that we want to focus on the alternative to the freedom population orbitals, and these orbitals belong to molecules and nanostructures where interatomic distances change over time, and this activity of interatomic distances brings this so-called rate of orthogonality and induces transitions. So we are doing practical steps to account for this assessment.
That's not what
Thank you for joining web. Just a second. You're what now?
Okay. Okay, is it working?
Yes.
Excellent. All right, so I am going to be going over, sort of loosely speaking, the definition of the Redfield tensor. And so any of the code that I'm showing here is coming from the correlation underscore v7 script, that MATLAB one. So first thing that we need is the non-adiabatic couplings. We've already kind of gone over that though, but this is sort of what everything else is built on. So just kind of a important tidbit to keep in mind. So we use those non-adiabatic couplings to compute our autocorrelation functions. And so, yeah, I guess I don't know if I really have like a good concise way of describing what this thing really is, but it sort of tells you how, if you have strong overlap here, and then you're likely to have strong overlap here again after some fixed like time delay tau, that means that the value of your autocorrelation function will be high there. And what we're mostly interested in, like this is technically the definition here, but we are going to be pretty much exclusively using m sub ij, because that basically tells us how, it tells us about orbitals I and j, and since we're talking specifically about transitions between those orbitals, that's mostly what we're after. And so there's kind of some approximations that we're going to be using to make use of this thing that makes our lives a lot easier. So basically, if this autocorrelation function, spikes up at some point for, some tau much bigger than 0, what that winds up meaning is that, say this is ij and this is ij here. That means that if you have strong overlap, you're going to have it again after that time delay tau. And that means that we kind of have to consider like the whole span of the of your trajectory. Whereas what we would rather have is if your autocorrelation just drops to 0 basically immediately, then that more or less means that there's no real correlation between having strong overlap and then having it again at some other fixed time later, right? There's no periodicity there. It's basically just random. And that's going to come in handy later. So this is the part of the code that actually does that. It's these core things here. So we're just talking about orbital I, orbital j, and then this value right here is equivalent to tau. And with MATLAB, instead of indexing things starting at 0, they index with 1. So that's why this +1 is here. And then this value here is precisely this value right here. And this is precisely this value right here. So this is where we're actually sort of collecting the data for this autocorrelation function. And there's sort of another way to view, this same information down here. We can instead look at it through like a Fourier transform. So a lot of times these autocorrelation functions will they'll oscillate, but the oscillations will damp over time. And that means that we can write it in this form here. With, this omega is just basically the frequency, there's no, it's just basically a placeholder. Same thing with this gamma. This just determines how fast it's going to go down to 0. So if omega is way bigger than gamma, then we are in the monochromatic case, quote unquote. So basically, this thing is going to have very strong oscillations at that frequency omega, and the Fourier transform, m of omega, will wind up depending strongly on sort of the whole trajectory throughout. Your whole trajectory, I guess. And that's, again, the case that we don't want, because that makes our approximation not valid. Whereas if gamma is way bigger than omega, then it's basically just a lot of white noise, just a lot of randomness. So then the Fourier transform will be roughly constant. And that really means that we only need to give a crap about the tau equals 0 value of this autocorrelation function, because it's at its maximum value and then it just drops down immediately. So we only really need to care about the initial value of it, because that's basically the whole thing. So with these autocorrelation functions, we can turn these into transition rates through these equations here. And again, we're only really going to be looking at the case of like ij, but these are, technically what the definitions of these things are. And so this omega is actually like a physical value. This does actually come from somewhere. That's just the angular frequency of a photon with the energy of this energy gap. So basically, if we're looking at the IJ case, you can see that the only difference here are these indices. So that would actually make these things equal to each other, which will be kind of nice again shortly in the future here. And if we are in the case where, our autocorrelation function drops down right away, then that basically means that the only thing contributing to this integral is, again, that initial value of our autocorrelation function. Okay, so this is actually the definition of the Redfield tensor, I guess, in equation form. And so if we're looking at, R sub ij, because we're only interested in the transitions between orbitals I and j, I mean, we can sort of implicitly assume that I is not equal to j here because we're looking at two different orbitals. Otherwise, it would be kind of boring. And that makes these delta functions go to 0. So we can just completely ignore these terms here, right? We just don't need to worry about them. So then we're just left with, this thing plus this thing, and those are the same things. So effectively what that means is that our value of the Redfield tensor is just going to scale with this, and this is roughly equal to this. So in the correlation script, when we're actually putting these values in, this is the Redfield tensor here of I, j, and since we're only looking at two orbitals, this is just a matrix instead of like a 4-dimensional tensor. And again, that just makes everything a lot easier to handle and visualize and much quicker to compute. And so we're using, okay. We're just using basically this value, which is the equivalent of the autocorrelation function at time 0, because this is the ith orbital, jth orbital, and this is the time value. And we're, again, since we're in MATLAB, the indexes start at 1. So this is the equivalent of time equals 0, tau equals 0. And this is just like a normalization constant there, so you don't really need to worry too much about that. And so that's how we actually wind up getting, the Redfield tensor out of our code. And then this is just kind of extra detail that I threw in here in case people are looking at it later, because we can, we can plot the Redfield, matrix, quote unquote, and that'll show us like transition rates and whatnot. But then we can actually go further and use the Redfield tensor, which is part of this guy right here, to figure out the time-dependent density matrix, which is, I mean, really what we're after at the end of the day. And then this is all just kind of, the pieces of this equation here, which is what we're ultimately after. And that is all I got.
Okay, please join me in thanking London. So any questions, either practical or theoretical? Oh, okay, someone wants to.
Yes, Braden would like to give me a hard time.
Maybe you can just read it out loud so that.
Oh, true, yeah. So Braden's first question, in my definition of the non-adiabatic coupling, is the equal sign correct? Should it be approximately equal to? Well, technically speaking, yes, it should be approximately equal to, because we're kind of taking a continuous phenomena and making it discrete. I don't know if that's kind of what you're getting at, but that is, I guess, the first problem that jumps out at me. But this is as close as we can get to the exact answer, doing this on computers with discrete time steps.
I think Braden wants something different. He's thinking about definition of Born-Oppenheimer approximation when there is a second order coupling.
Oh, yeah, I suppose.
Braden, is it what you wanted?
Actually, I think I might be wrong because I thought this expression was the finite difference one, so maybe it's okay.
Okay. Let's look for the second question of Braden.
So the second question, what's the physical significance of the two gamma and PM terms? Oh, plus minus terms. That must be what that is. Specifically, the plus minus rate of absorption / emission of the phonon. I used to know the answer to that, but I can't remember it off the top of my head. Because there's a reason that you're looking at basically your first set versus your second set. And I believe that it basically has to do with like an upward transition or a downward transition, which would correspond to absorption and emission. But I would have to brush up on this to like be able to give an answer with confidence, I guess.
Right now, you satisfied?
It's fine, yeah.
And Dimitri is asking why the electron photon interaction comes in the second power. Where are we looking at the second power? Are you saying like a something squared term, or did you mean something else with second power?
Last slide, please.
Ah.
So you do have this R Redfield tensor term that controls dynamics of density metrics, and Redfield tensor is proportional to interaction squared. Why not interaction to the first power?
Could you say that again?
So the in this slide,
Yeah.
the R with 4 indices is proportional to the second power of electron photon interaction. Like V times V at different time, and then some Fourier or whatever transforms, right?
Okay. Yeah.
Why this equation for density metrics does not include the electron photon interaction in the first power? Because if it is all based on perturbation theory, one should start with lower powers. Why one immediately jumps to the second power?
Well, I guess my gut tells me that we're talking about like transition rates here and like time dependence, and usually that involves like a second power. That's probably not really
Okay,
the answer, but
the first power can be included, but it will be giving zero contribution after average or trajectory, because it fluctuates by sign, and first power just washes out after making averaging procedure.
okay, yeah.
We have very advanced discussions. More questions to one. Questions 1, questions 2, questions 3. Please join me in taking the line one stage. Okay, you can stop sharing. Many thanks for presenting and supporting. So, Alessa, will you please share your screen?
Okay, so Landon went through a lot of this and much more theoretical and technical detail. So I guess some of you will look at the autocorrelation function a little more. So up to this point, we all had our models we started working on. We repeated it. We've done the molecular dynamics. We worked on the non-adiabatic coupling. The next step is doing autocorrelation function calculations, and those will be able to be used for the Redfield tensor, and then we can use those for observables. So generally speaking, correlation functions in general describe how different quantities compare at specific points in time or space. And a differential equations class, for example, you may have heard of convolution. If we're looking at an autocorrelation function, that's just when we have a quantity that's being compared with itself. So credits to look at the Wikipedia page that describes it. It gives this like visual example of if you have a quantity that for quantity G, if you just look at the F, that would be an autocorrelation. If you just look at the G across start with itself, that would also be an autocorrelation. For non-adiabatic couplings, we have this expression. We have these from which are from our non-adiabatic couplings. The T here represents the duration of the trajectory of the molecular dynamics. Note here it looks like an average since since an integral can be like a sum, you're going over all points, then you're dividing by the total trajectory. There's been some comments about this first order, second order correction. So again, like the reason we do this autocorrelation function is that it provides a first order correction approximation for the non-adiabatic coupling for the electrons according to time dependence perturbation theory, and second order correction perturbation with respect to the electron nuclear interactions. Perturbation theory from quantum mechanics just tells us like it's difficult to get an exact solution, but you can find it's a method of finding an approximate solution. And since we're dealing with complicated systems, these approximations are computationally more effective, and they can help us get pretty close to what we need. So once we have our autocorrelation function, we do a Fourier transform as we commented on. We have these two pieces, and from those get used into the Redfield tensor, and the Redfield tensor is then used to compute the electron dynamics as discussed. With the MATLAB scripts, it will be presenting more on this later. I just wanted to visually demonstrate what this correlation functions may look like. You can look at different the transitions between different HOMO levels over time. And this also can be put together to visualize the Redfield tensor. Since the autocorrelation function forms the matrix elements of this, and I think something else to visually demonstrate from this, since we're dealing with an averaging, the more points you have, the more things can smooth out. So if you contrast having a few data points or like position snapshots compared to like 6 compared to say 400, you notice that things smooth out more from the averaging. So that's all I have to present on. Open up for questions.
All right, let's take the any questions in the audience or online? Let's look for the chat line.
So I can see Dr. Collins asked what system and the autocorrelation function was computed for. I commented on the slide. It's a cadmium selenium nanocrystal and a lead selenium nanocrystal that are slightly or spatially. And I think that's the model. Yep.
The question is because right now in the next few talks we will see several examples of these functions on one hand. Another one was sharing expectation that it should look like oscillatory and at the same time decaying function. And we may not as big theoretical scientists, but just by observation to see connection between features of systems and this oscillatory / decaying behavior. So intuitively, it is expected that the smaller the system, it is more oscillatory and less decaying. Maybe you'll find otherwise.
Since the system is bigger, or
If it gets bigger, it will have less oscillations. It will decay quicker. By expectation, maybe there will be some surprises.
and you have a question: how do autocorrelation functions match with Landon's prediction of cosine omega t, e gamma omega t? Is that a rephrase of the same question, or is that a different question?
We agree that one can think of your numerical data as a cosine times decaying exponential. Okay, good.
And was my diagonal, vector tensor larger than the out diagonal elements? I guess my thought is, if you have since these matrix elements are based on the autocorrelation function, which creates similar snapshots in time, if these correspond to different bands of the model, like the closer the transition elements are, the more probable they'll be. So, like, for example, like you're further out you go, like further out you may be from like energy bands high, less probability. So it's more closer, like the things are close together, but less far away.
So the closer their energies, right?
And yeah,
Okay, so if resonance conditions speed up the transition. If energy of initial and final orbital are very close, then transition will be quicker.
okay, yeah.
There is a question from Sean, and then there is a question from David.
What are the dimensions for the spherical tensor model? What dimension is time on? I'm not very familiar with how these Redfield tensor figures work at this point. I know that for the autocorrelation function, you have rates of time. So I guess I do not know for sure at this point what the, or I just know that like the z-axis represents the like amount of energy or the intensity.
It should be in inverse time.
Inverse time.
Rate, how quicker electron jumps from one orbital to another one.
Oh, okay. So that
With
would
like
be,
second inverse seconds or inverse femtoseconds. Sean, are you happy with the answer? Thank you. And there is a question from David.
okay. Why does there appear to be a gap on your main diagonal? I guess that's a good question. And then I don't know if that corresponds to the. Well, that wouldn't make sense. I don't know. Would it make sense if that were the homoluminal gap or no? Okay.
The bigger the gap, the bigger offset and resonance condition is not met.
Okay. So then,
Then it's solved.
okay. All right. Does that answer your question, David? Okay. How sensitive are the elements in types of the ground state dynamics?
Let me try to answer because Braden, they shouldn't be sensitive if the step is short enough, because it is a like definition of derivative. The limit should converge if the time step is small enough. But in our subgroup, no one checked it because it is very expensive computation. So it is a good idea for theory development paper. Of course not. It's expensive. One needs to redo things again and again with smaller and smaller steps. Yeah, thank you for the question. More questions to Hadessa online, in the audience or chat? If not, let's thank her once again. And the next one is Granlie. So from now on, there will be some overlaps, but it's only a plus. So because we are progressing towards becoming experts in this subject.
All right, so I guess I'm kind of presenting with the same sort of stuff as working on calculating autocorrelation and this Redfield matrix. So kind of like Adam was covering, we got our input files that you can see there. And the HOMO, min-max orbitals and time steps that you'll need to change, depending on what files you have. And like we've talked about here, here's the equations that we're kind of calculating in these two different lines. One thing to notice is that if you're changing your time steps back here for what files you're reading, you are also going to have to change those in this for loop here. And I guess just kind of jumping ahead, we have like the actual graph of the autocorrelation function. This just kind of like justifies our approximation, I guess. Assuming that the autocorrelation goes to zeros, then we kind of simplify our matrix by a lot. As you can see very clearly, the functions all drop to zero within 1 or 2 time steps of tau. And if you have to create this sort of graph for any sort of reason, in the correlation MATLAB script, you can see the lines over here. The only things that you need to change is like what you see in this red circle here. All of these like data points are already pre-calculated above this line. So you'll just have to change what HOMO numbers you have here to be able to change what the plots. And at the bottom, you also have the legend that gets created, so you can make it all nice and pretty. I guess that's kind of what I have here, and then I guess also like Hadassah did, you can visualize this matrix. And something to notice here, I guess, is that the axes numbers aren't corresponding to the band level specifically, but they're corresponding to how far above the minimum band you are. So like in my example, 0 corresponds to 296 because 296 was the lowest level that I have. That's all I have.
Great, let's thank you. I learned something new. I never knew how to do legends in MATLAB. Thank you for bringing it up. So, what was the system so that it shows quite noticeable oscillations?
Yes, so that is thanks to Adam's data because I had a mishap with my coupling files. So Adam, do you want to speak on what model you were working with?
Yeah, this is a porphyrin donor bridge acceptor system. It has a zinc porphyrin, zinc 2 porphyrin on one end and a free base porphyrin on the other end. And the bridge is like 3 repeating units long. It's conjugated, so electron transfer can happen over the bridge.
So to see the oscillation of the system should be either very small or very flexible. So is your system very small or very flexible or both?
It's quite large. But it's not as large as a nanoparticle or something, but it's in comparison to just looking at like a smaller coordination complex like the titanium hydroxide or something. It's a bit larger, but its bridge is meant for it not to bend too much, but you can still see some a little bit of flexing. Yeah, a little bit of like twisting and flexing with the bridge. That's it.
Thank you. Nice administration of the questions. Any more questions to Joseph?
Just make sure I said on the Redfield tensor graph, like the X, so the Z corresponds to the transition rate probability. And then X and Y are the
Like how far above they are from like the lowest orbital they have from like energy pump.
So like they're the energy pumps or I think the position that they did the energy pump.
They're the like band levels, I guess.
Indices of orbitals.
Yes, yeah.
And it would be reasonable to relabel, like starting from whatever 280 or
96. Yeah.
and band energy or synonymous in this case for band field.
Well, here is discrete integer, it's just number of orbital. Instead of absolute value of energy, just number of orbital. But then what can do histograms and if orbitals are degenerate, then such graph will be. If you want to have x and y exercise energies, orbitals, if you have too much ambiguities for degenerate orbitals, so it's safer. You just index. Thank you. Questions? Anything else to ask for Joe? 1, 2, and 3. So up to now, and in the next few presentations, we will on the paired spins when each orbital has like one spin up, one spin down, and therefore we don't care about it. But very often practical systems have unpaired spins. And in this situation, one needs to make some adjustments to all protocols. So the next speaker, Sarah, will share his screen and teach us what to do if spins are unpaired.
Yeah, sure. Thank you, Dr. Green. Hello, everybody. I'm going to talk about how to convert the couplings to the RRR file, as other speakers said, but for this case of spin polarized. So as other students explained, in addition to the MATLAB file that we need 2 other files, energy pop and the coupling files. But one thing that you should keep in your mind is that before downloading your coupling files, you need to unzip them using this command gunzip and the name of the couplings file. And then after downloading your coupling files, I mean the decompressed coupling files plus your energy pop, you need to import these files into your MATLAB code file. So you need to define the range of desired orbitals and the number of HOMO for each of your spins. So you need to repeat this procedure 2 times, one time for the spin up and the other time for the spin down in a separate directory actually. So here you, as others says, you import the energy pop file. And then here you need to specify the range of the coupling file that you have. In this case, I have 360 coupling files, and also you need to specify number of steps you want. So for my case, it's 359 steps. So this is the output after running your MATLAB codes. This shows the Redfield tensor in case of the different transitions from, for example, the orbital I to orbital J. This shows, I think, the probability of between the different transition states. So you need to repeat the same procedure for spin down in its directory. After all, you have a RRR file, which looks like this. So it has, it's a kind of matrix that the number of rows and the number of columns are equal to the number of transition that you had in your energy pop file. So for my case, for the range of the energy that I specified as a mean and the max orbital, as in the first lines of that MATLAB code, I have 42 different states. So I have 42 number of rows and 42 number of columns in the RRR file. And one point is that the diagonal for the R for each transition is 0. For example, transition from state 1 to 1 is 0, 2 to 0, 3 to 3, 0, and so on. That's all. Is there any question?
Okay, please join me in the next step.
Thank you.
So, who has unpaired electrons in his or her system? If potentially. Maybe it's just okay. So, then we will. So, any questions to Sarah?
So the question in chat, Dr. Killen asked that does energy profile are different from for spin up and spin down? I think yes, they're different. If you want to take a look at each spin separately or individually, yes, I think it's different.
So you do calculations for spin up and spin down in different directions, right?
Yes, actually, yes, definitely. As I said, we need to repeat the same procedure 2 times in 2 different directories. One is spin up, the other is spin down. As I explained last time, yes, we have also different couplings file for spin up and spin beta. They're completely different. And then the other question is, where does one receive the value of HOMO for alpha and beta spin component? We need to take a look at our energy profile. So then we understand what is the HOMO for the alpha or what is the HOMO for the beta spin. So they are different. So for my case, for example, the HOMO for the spin up was 196, while for my beta spin, it was 197. And then, would it be correct to say that for alpha and for beta, the procedure is the same? Yes, but the procedure is the same, but the energy profile, the coupling files are different. And also this number of HOMO orbital also is different. And what is located on the main diagonal of the RR?
When 2 indices are equal to each other.
Yeah, it is 0, as I said. For example, here, the transition between orbital I to orbital J, 0, orbital I, and I mean the orbital 1 to orbital 1 is 0, orbital 2 to orbital 2 is 0, orbital 3 or to orbital 3 is 0. When the I and J are equal, yeah.
Many thanks for enthusiastic answers. Let's double check if anyone online or in the room to check anything. Oh, sure.
Does the charge system pose any problems for doping the spin-polarized? I'm not sure about this question. Actually, I don't get the meaning of the question. Does the charge system pose any problem?
So
For doing
unmute the microphone and tell a little bit more about the question.
I was just wondering if it would pose a challenge to do this on a charge system, but I don't think it will. I don't know.
I'm not sure about this, but I think the same as you. Yeah, I think there shouldn't be any special problem or challenge when our system is charged. But I appreciate it if Dr. Killing can help.
I also don't see the problem. So if one changes charge by not by two electrons, but by one, then we will run into unpaired electrons, and we will need to take care of the spin polar. We will need at least spin polarized description anyway. So Lola, you have some question?
No, I was just gonna say, I don't think it will cause any problem. You just need to like add the line in the in card that specifies that it's a charge system.
Okay, thank you.
Thank you.
Okay, Braden has a new question.
Yes, pardon. Yeah, Braden. Yeah, he asked about. So we have two rate for alpha and beta spins. Yes, we have two rates.
Yes, Braden, the answer to your question is yes. If we decouple, if this spin alpha and spin beta components are independent, then it will be independent rates. And to couple them together, we need to wait until the last but not least talk and hear to David Graupner. Good message.
Thank you.
More questions to Sarah. One. More questions. Two. More questions. Three. Let's thank Sarah once again.
Thank you, everybody.
Nice talk, stimulated, very healthy discussion. So the next presenter is Amara. Amara, will you please share the?
Yes.
And I think Amara goes back to paired number of spins, but she will help us to look on a slightly different angle and several. I think this will be intrigued when Amara will tell which model she is describing.
Yes. Okay, so this is the background of the Redfield equation and the autocorrelation function in the non-adiabatic coupling, and many previous talk have explained in detail about these equations. So these are the input files that we need to run the MATLAB code, and we need these files in the same folder in which we have the MATLAB code, and these are the different MATLAB codes that are in that directory. And I didn't calculate the spin orbital correlation, but I think that these the V3D and V3F codes are required for the spin orbital calculation. But I use the correlation V7 code for this calculation, that is the spinless calculation. And this is the in MATLAB code, and as everyone explained earlier, these are the orbitals, HOMO, and these are the HOMO orbital, and this is the maximum and minimum orbitals in the file input overlap that we provide. And here this is the loop of the coupling files information. That is for my case, it was from the 3 to 85. So after running the calculation, we get this RRR file that is it is the format that is explained by the Sarah in the form of the matrix and the diagonal matrix. So this is the output of autocorrelation function, and this is the MATLAB code, that part of the MATLAB code which gives us the information how we did the information like HOMO to HOMO -2 to HOMO -1, and we can change it accordingly. And this is the representation of homo minus 1, homo minus 2 to homo minus 1, homo minus 1 to homo, and homo 1 to homo 1 to homo minus 2, as explained in this code. So, and there was a sudden decrease at the initial time step in the autocorrelation function. And then it is due to the correlation from, it is due to the, I think the MD simulation at the temperature. So this is the representation of the Redfield tensor that is based on the MD trajectory, and this is the little bit information about that. The transition rate between the any pair of orbitals should be less than 0.0 per femtosecond. If it is less than 0.05 femtosecond, that it indicates that the quickest pathway of the phonon assisted transition is the slowest than the adopted Rabi frequency in the TDS-MD simulation. So Rabi frequency is the radian frequency of the Rabi cycle of the given atomic transition in any given light speed. So that's all from my side. If you have any question, feel free to ask.
I appreciate you thinking about it. So, any questions in the room? Any questions? Fine. Any questions in the chat line? It looks like everything was crystal clear, so we just solidify our knowledge on the subject. Many thanks, Amara. So just let's count down once again. More questions. What? Yeah, please.
What was the model? You said, or Amara, what was the model you were making?
It was the CNT with the MN, its MN indices was 11.0, like chiral CNT.
Okay.
Okay.
More questions. One. More questions. Two. More questions. Three. Thank you very much again. So the next presenter is Lola. Lola, would you like to share a screen?
Yes, so you need to enable sharing.
Let me check. Oh, you logged out and logged in. Okay.
Yeah.
Now you're of course.
Okay, so I will be talking about visualizing the correlation function. So here I'm showing this shows the representation of the coupling between the electronic state I and J, and here I'm showing the Redfield equation that sort of like explains the time evolution of the density matrix. And what you're seeing on the right here is the energy dissipation, which explains the energy that is lost between the weakly coupled systems and the environment. So here, this RIJLM is the Redfield tensor. And the Redfield tensor is generated by converting the non-adiabatic couplings which have initially generated to rate of transitions. And you have to do that by Fourier transform of the autocorrelation function. So here I am showing the things that you need to run this MATLAB script for generating the RRR. and you need the energy pop, which shows like the orbital numbers with their energy and occupation. Then you need the coupling files that you have unzipped. And you just need to look into the input overlap file to check for what your O-min and O-max is. Here I'm showing the MATLAB script on the left. This is where you input the HOMO and yes, and then this line is your O-min, which I think means minimum orbital. You sort of like take that number by subtracting 25 from the HOMO. It's not necessarily 25, but 25 is just enough range. And this is O-max, which is the orbital number when you add 25 to the HOMO. And here is the coupling files, depending how you decide to name your coupling files and how many you populated. So I'm showing 999 here because I had populated 999. If I had done more than that, I would go on and do 100 to 999. If I had done more than that, I'll just like put the number here and also increase the number of couplings that the script has to look through. And this is what it looks like. This is what the Redfield tensor file looks like with zeros on the diagonal. And here I'm showing the RRR. Here is the rate of jump. Here is where you have your LUMO, and down here is where you have your HOMO. In this system, the HOMO and LUMO are like strongly coupled. That's why you see all of this, they're like very close to one another. Braden had written this script in Python, which is like super easy, where you have, so here I'm showing the folder where I have populated my couplings and my single point, which is the same thing as the PXX folders that you generated initially in the calculation. You just need to run that script and it generates this file called Redfield tensor output. I'm having to here because I did different calculations using PBE and PBE0 functionals. So here on the left is what it looks like. And this also tells you what the HOMO is. So if you look, 87 is somewhere around here. This is like the HOMO and the LUMO. And you can see that like it's strongly coupled. It's showing this intensity here, just like the previous image. Yeah, that's all.
Okay, this Jenny, thank you all. Okay. Any questions in the room? Or online?
I put this file path just in case somebody wants to use, like want to try out using the Python script. So you could just go in and just grab it.
Oh, thank you. Thank you. It's kind of you. Was it like cooperative work with Braden to generate this?
What did you say?
Was it cooperative work with Braden?
Yes.
Lobster script.
Yes, it was cooperative work with Braden.
Okay. Yeah, thank you, Braden. Thank you. So how different is this lobster from the skyscrapers on the previous on the slide 4? Is there
it's not
differences like?
It's not very different because like the intensities here are shown with the height of the bars. Why here the intensity here is shown by the brightness in the how bright it is. Because if you look towards here, it starts to like get dark.
So it's different representation of the same object, or the objects are slightly different?
No, it's the same thing. It's just different representation.
Okay. And David was asking question to Hadassah, why the HOMO-LUMO transition is much slower than others. Why the intensities of transition between orbitals are irregular. And in your system, you do have a lot of low rates. Like if you go to previous slide, this skyscrapers. So there are several low intensity transition, not only on the HOMO-LUMO, but along the diagonal. So what's the reason? Yes, what is the nature of these transitions, and is there any connection to structure of your model?
So they are, I believe they are low because like there's sort of like a fast recombination between the within the gap, and it's also a function of the system, I believe. Yeah.
But what is the system? Can you describe it by words?
The system.
So picture.
I don't have a picture of the system. It's an organ.
Like, is it a solid nanostructure?
Or it's an organometallic complex. A transition metal complex.
Okay. Does it have a lot of sub-gaps? Not only fundamental gap, but sub-gap between like LUMO and LUMO plus 1?
Does it have a lot of gaps? Is that what you said? No, it doesn't.
Okay. Thank you.
All right.
There is a question from David.
Was the range for the RRR graph adjusted to show the HOMO-LUMO?
It looks like a skyscraper graph, especially when you compare it to the lobster graph, that you're not actually showing the HOMO-LUMO on the skyscrapers. It looks like you're down at the tail of the lobster.
Yes, so this was adjusted to show the gap because like it's easier to like for us to be able to tell where like the strongly coupled where it's coming from, because from here you couldn't exactly tell like what the HOMO-LUMO is. Because like looking at this, one that's able to say, oh, like which transition exactly is this one, which one is this one, but that's what this helps you to do. Did I answer your question?
It looks like Braden is stating there's the exact same question as I am. And it looks like the skyscrapers graph you're showing deep in the valence band, or maybe not deep, but in the pure valence band. It doesn't look like you're showing the HOMO. Like if you go up to slide 3 quick.
Maybe I had labeled this incorrectly. This is just supposed to show like the valence and conduction bands.
So if you go to slide 3 quick. This MATLAB code that you have input here, specifically the HOMO, OMIN, and OMAX, Right, that actual system that you're showing the results for?
So this one is showing for this, but I'm not exactly sure if this is the same one.
Okay,
Okay, yeah.
so then I'm not entirely sure if my question is valid or not. I mean, it's still valid, I just don't know if we can answer it with the knowledge we have.
Yeah, probably for comparison, we need to review them with the same range. So there is a question from Braden.
My graph is only showing deep valence bond coupling between indices 0 to 20.
Okay. So it's to some extent was already answered. So
Yeah.
questions to Laura in the room, online, in the chat line. Last chance. Questions 1, questions 2, questions related. Thank you all. Once again, we feel stronger and stronger in this subject. So we have 2 presentations more. So next one will be by Amir, and I believe it will be without spin polarization, we will play with spins, but slightly different aspect and very unusual system.
Can you hear me?
Yes.
Very good. So, thank you, Dr. Killian. I think, so sorry, which, okay. So I think everything is reviewed by other students already. So maybe it's nothing new. As Dr. Killian said, I don't know, it's complement or compliant. It's, we just use this non-adiabatic coupling without a spin for a 3D condensed conjugated polymer system. Let's just review the process here. So we just had the geometry optimization. We heated up the system later and then run the system to have molecular trajectory allowing the time. And then we, in the last week, actually, we have the knowledge transfer session, how to do coupling calculations and have coupling files. And today, the focus was on the how to visualize the Redfield tensor and calculate autocorrelation function. So here we develop a 3D condensed periodic model to investigate the PM6 conjugated polymer. So PM6 is kind of high performance semiconducting polymers. Polymer usually used in the organic solar cells. So in this part of the project, we perform non-adiabatic couplings to take a look, to explore the charge transfer between the polymer chains. So we have multiple systems. So this is just a pure polymer. And in future, we will have the blend of this conjugated polymer as a blend with some acceptor units. So this is kind of practical usage of non-adiabatic couplings for the photovoltaic performance of the solar cell materials. So I think this, again, not new. So we, to have the visualization, we need energy pop file. So we know the range of the orbitals that we want to plot in this visualization, and we need to have, as Sarah said, coupling files, get them unzip it. There are several comments. I usually use these 2 comments to unzip files and have them as a text. And next, you need to save all coupling files in the same directory next to the MATLAB file that you are going to use. And the only difference that I made some changes in that MATLAB file. So you just need to put the energy pop next to coupling files in that directory, and then it will automatically just read the minimum and maximum orbitals and find the HOMO orbital. I'm not sure if I copied that in that MATLAB directory. If not, I will save it today. So feel free for no spin calculation. If you want, you can use this file also. Kind of those manual changes are automated. You just need to specify number of coupling files and also number of time steps that you are going to do your calculations. So yeah, again, before running the code, you need to make sure that in the same directory you have coupling files next to the MATLAB file and also having the energy pop file. And after running that, you will have the RRR file that actually we have the Redfield tensor elements in this matrix. So the size of it's a square size matrix, and the size should be the same size with the number of rows in the energy pop file, actually the number of orbitals that you specify to do the coupling calculations. And I think it's redundant, just we can have the visualization of the tensor elements. And this is the Redfield tensor for this PM6 3D condensed polymer, as you can see here. And also for the autocorrelation, I had, so far I just finished 400 steps in my coupling calculations. And we need to have a quick decay after the starting the simulation. So far, considering the time step of 0.5 femtosecond, after near 200 femtosecond, we can see that the system is fluctuating around the 0. So I'm sure that you do not have any question because there was nothing new here. But by the way, thank you for your attention.
I think, who knows, maybe there will be questions. And I give a special thank you for your intention to share the code. And I see the hand of professional, elegant programming that you're doing in the lines that you did show.
No problem. Just one question. I wanted to copy the file before the meeting, but I didn't have access to Photon. I don't know, Photon is down for any problem or it's my problem? I cannot.
I was told that full time was down right now.
I wasn't told anything. But yesterday there was a discussion that engineers who build the chemistry building need to rewire something quickly, or
that's Thursday. So
it's related. So
not that I know of, we need to, and this is mainly for Stephen, we need to shut down Photon properly tomorrow.
Okay. So
because they're coming and unplugging everything that's plugged in on Thursday.
Okay. So whoever computed couplings and downloaded them to personal computers are a little bit more safe. If something happens to put code, if you provide successfully. So any questions to Amir, either in the room, online, or in the chat line? So, I mean, I have a curiosity and question that I don't have answer for. In your image for autocorrelation function, there is a quasi-periodicity of the blue lines. They show spikes, then go back to 0, and then it looks like something oscillates. So, is there any connection between frequency of these oscillations and anything real in your model? Is it related to maybe frequency of CH oscillation, or it is completely random things? Just your opinion or your hypothesis?
Thank you for your question. I need to double check for which orbitals we have this blue plot. So, but I'm not sure. You think it's due to fluctuation of the specific bond between the atoms, or?
I don't know. I do not have enough background knowledge to remember from the top of the head what the frequency of CH bond, but it should be like 20 femtoseconds.
I don't
So,
know either.
and I wonder what's the reason, because it looks not very random. One may identify some period of the oscillations and just it will not affect the subsequent calculations, but just analysis of results. Like why this way, what can you learn from this frequency?
I do not have a certain answer for that. So let's have the results for some other models also. Then if we see, if we have similar observation, then we can have more evidence to talk about. So I'm not sure if we repeat that for another organic polymer, we will have same results or no.
Okay, thank you. More questions on either protocol or analysis of results? Good questions. Please join me in thanking Amir. Many thanks for not only contributing to knowledge transfer, but also showing original results on a new system. Okay, and last but not least, Dave, you like to share your screen? So, special talk, the only time in our session when we speak about non-adiabatic and non-collinear speed with spin orbit couplings.
So I am like everyone else, we're looking at the correlation code. I was specifically using version 8B, which you can find in the bin on NERSC. I think it's in the bin on Photon, but I'm not positive I actually copied it there. I know it's in the bin on NERSC. You're also going to need the energy pop and the coupling XXX files, like it's been mentioned. So here is the beginning, the start of the MATLAB code. So like it's been mentioned, you have the HOMO, the OMIN, and the OMAX, which are the HOMO, the lowest orbital and the highest orbital you're looking at, and those are the VASP indexes for them. Then in the green boxes, I have the couplings. So you just need to make sure that they match how many you have. So in this case, I had 1,500. And then in the blue box, you have time steps. And what you want to do is you want to make sure that this big number here matches the highest coupling you have. So in this case, it's 1,500. Assuming you have all these minus ones. If you don't, you have to calculate it properly. So then if we actually dig into the MATLAB code, this is the portion of the code that generates those bar graphs that we've been looking at. The skyscraper graph, as I've called it a couple times as well. So if you look at this, you see that we have these two sets of numbers here. These are the numbers, specifically this top one, that you want to adjust to make sure that you have the range you're interested in. So you're going to put in the HOMO, theoretically should be somewhere in the middle of that range. And then this lower one, you need to adjust. This is the axis count. So this is determining the size of your X and Y axis, which you want to be the same as this range. In the blue here, I have the names, the labels you give the axis, because it's significantly easier to change them here and make them look good than to do it later. You can do it later, but it's much easier to make them look good if you do it here. So then if we continue, and after you made your graph, you can open the property inspector, which is in the view tab of the figure. And under ticks, you can adjust the actual locations of the ticks as well as what they're called. So you notice that in my graph, I have them labeled as HOMO -10, HOMO -5, HOMO LUMO +5, and LUMO +10. This is where you would make this adjustment. You can also, if you screwed up the range of the thing, that would be adjusted under rulers here. You could adjust those labels, like I mentioned, under labels. So this has a lot, the property inspector has a lot of access to play with what the plot ends up looking like in the end. And it's not what I meant to do. That's basically the end of my plot. The other thing to note with this script, this print line here actually saves this plot as a PDF in your file. So if you want to open it later and look at it. Otherwise, that's what I have.
Okay, please join me in thanking Janet. Someone was clapping longer with CLA, especially excited by the story. Okay, any questions in the room? Maybe you since you were clapping longer. Anyone in online? Okay, then let's go to the chat.
Okay. Dimitri asks, does the format of energy popping coupling files differ from the ones for paired spins, or the format is the same? Format is the same.
So basically, one can use your scripts for paired spins without any.
So I went through the coupling version 7 that you sent out. The only difference between coupling version 7 and the coupling version 8B that I used is how they treat the figures. The math itself is identical.
Okay.
Why the index for loops over time have durations shorter than the length of the trajectory? It's because of how it's because tau is 1 less than t in the end. If we look at our calculations, and I did not include that line from MATLAB that Landon had that actually calculates the core equals whatever line. That actually shows you how it calculates it, but it's because of how t and tau are related to each other.
Okay, so,
And I don't offhand remember how it is without looking at the line.
so you just do not want to set up indices that will drive us away from the area of definition.
Yeah.
Okay.
Short of that. Dimitri, standard traditional question, why the heights of the skyscrapers change, high, low, high, low? So if we look at this, you see that we have this alternating pattern of peaks. This is indicative of a spin orbit calculation because spin orbit has degeneracies for all the orbitals because it's treating the spin up and the spin down as a single thing that is as 2 separate bands within the single calculation. So you end up with very high interactions between those near degenerate orbitals and not so high and lower intensity around it by comparison. So I did not show it here, but there is another version of this script that does the z-axis here in logarithmic scale. So you can see height on the other peaks much easier when using that. But it tends to drown out this central peak area here. Kaya asked, why do you start doing RR calculations from 17 to 36 instead of 1 to 36? So the RR is calculated for all of them. I'm loading in 17 to 36 because that's the range I'm interested in. That gives me HOMO minus 10 to LUMO plus 10 or whatever this model was. So if we go back here, we see that we input values, and this is not the same model as the one I'm showing the graph for. So you see that my O-min here is 80 less than my HOMO. So if I wanted, let's just ignore that for a second. Let's assume that my range is I'm calculating for HOMO minus 20 to LUMO plus 20 instead of minus 80 plus 80, because that's apparently what I did here, or something along those range. I'm only interested in plotting portion of it for this graph. I could plot more of it for a different graph. It's just I've aimed for this so you could actually see detail. So it's entirely just, that's the range I was interested in plotting. There's no grand scientific reason for that.
Thank you, Kate, for the question. Thank you, David, for answering. Is there anything else anyone want to? Yeah. Thank you, Kate, for saying the same thing. More questions today, online or in the room, or in the chat line. One questions, two questions for the 10 day landscape. Many thanks to all the speakers and participants of the whole discussion. So basically, we are done. I will announce the next sign list. Well, I'll try to do it as soon as possible, but last time it was announced on the night on Sunday to Monday, but I think it didn't degrade the quality of talks. I'll try to do earlier, but I think even a little later is okay. And in the series slides that several speakers were showing today, you have seen the equation with time derivative, which looks similar to a time-dependent Schrodinger equation, like ddt, then rho, and then something on the right. So the time evolution, time dependence of the density operator of the density matrix, which so next meeting we will speak about numerical ways to solve this equation. And the main difference from the time-dependent Schrodinger equation is that in Schrodinger equation the energy is conserved, and the equation that we are going to solve next week will violate energy conservation, and it is another subject of discussing. Like, who are right? Our research group or the whole world think that energy is conserved? Was there a way to find the truth in between? And in 2 weeks from now, we will make another meeting how to convert solutions of this time-dependent density into observables that can be compared to experiments.